So next topic in third unit is loop time, subroutine, timer to interrupts. Okay, I think you all know what is loop. What is loop? So a small program or small task which will be called often in the main program to execute for several time. That is said to be loop. Okay, so the loop time will be maintained by the timer circuit. Okay, so based on the time set in your timer circuit, it will be taking time for the execution of loop. Okay, so now we are going to see all this topic. So a 10 ms, that is 10 millisecond subroutine was used to insert a 10 millisecond delay into the main line loop. So in the main program, you are going to insert a 10 minutes delay by giving a loop program. So this delay plus the execution time of the blink subroutine resulted in a loop time only slightly longer than 10 millisecond. So if your delay exists more than 10 millisecond, then it will be called as a blink subroutine. That will not be called as a 10 millisecond subroutine. Okay. If your delay is 10 millisecond or within 10 millisecond means it will be called as a 10 millisecond subroutine program, unless it is not 10 millisecond means it will be called as a blink subroutine. Okay, consequently it was possible for the blink subroutine to decrement a scale of 50 counter once each time it was called, and to use this counter to blink the green led every time the counter reached 0. So in this case you will be using counter circuit for counting purpose. Okay, for executing the loop, each time it will be taking count value. Okay, so scale of 50 counter will be taken for the each time it is executing the particular subroutine program or loop. Okay, whenever it is called by the main program, and then when it is reaching the value 0, that is counter value 0, it will be blinking the green color or green led. Okay, when it reaches to the when the counter value reaches to the 0 value. So using this approach, the loop time can be used to control the timing of relatively slow event with a timing resolution of 10 millisecond. Unfortunately, as the number of tasks performed by subroutines called from within the mainline loop grows, the loop time also grows. Okay, so how many times you are taken for executing the loop will increase the loop timing also. Okay, the loop timing will be added to the total execution time taken for executing the main program. Okay. Accordingly, events that are made to occur after some number of loop times will occur more slower than if the loop time was actually 10 millisecond. If the loop time is below 10 millisecond means it will not take much more time for executing that program. But if it is more than 10 millisecond, it will be somewhat slow in the or delay in the main program execution. Okay, so so in this chapter, the timing of events will continue to be controlled by multiples of the loop time. So multiple number of loop times will be controlled by the timing provided by the timer circuit. However, instead of using the 10 millisecond subroutine to insert a fixed 10 millisecond delay into the mainline loop, one of the PIX3 timer will be used to keep track of time. So instead of using the 10 millisecond subroutine program which will be fixing the 10 millisecond delay in the main program, So instead of that, the your pick controller going to use three timers, okay, for tracking your time, executing time, okay. Task can thus take advantage of an accurate time reference to control the timing of events that are slow by peak clock cycle standard, but that may still need to be forced by human standard. So the advantage of using these three timers are nothing but it will make your pick device to run fast, okay, rather than making your device to slow down. It will be fast, okay, by using all these three timers, which will be tracking the execution time of the program. So as an example of such timing is given, a keypad used to enter setup information into a device needs to be pulled for changes often enough to detect each press and release of every key. So here, when you are using the keypad in the PIC microcontroller for entering the data or input, okay. So whenever you are pressing the key and releasing the key, the time taken for pressing and releasing the key will be detected by your timer circuit, okay. On the other hand, the polling needs to ignore what look like fast successive presses of a key resulting from the key bounds associated with mechanical key switches. I think this key bound technique you have learnt in your microprocessor and microcontroller subject itself. Key bounds is nothing but if you press the key, it will take your keyboard will take or timer circuit will be counting the time for that key pressed, okay. If the key is if second key is not pressed in that particular time, then it will consider the first key as the input, okay. So அந்த time period குள்ள இன்னொரு கீயும் press ஆயிடுச்சுன்னா it will be taking the second key only as the input, okay. So that timing waited for your key press, okay, uh, is said to be key bounds. The time taken for accepting the key as the input will be called as the key bounds, okay. Since most key switches have a maximum key bounce time of less than 10 milliseconds, so for each and every key switch the key bounce time will be 10 millisecond only, less than 10 millisecond only. So checking a keypad every 10 millisecond means that if a key is newly pressed during one check, its key bounce will have settled out by the time of the next check 10 millisecond later. So on the 10 millisecond skulla, if you have any other new key pressed, okay, then it will be taking 10 millisecond extra for key bounce, okay. So the timing of some task is controlled by an external event or by an event taking place within one of the independent resources inside the PIC microcontroller. So some other task will be controlled by an your timing circuit for the external devices also, okay. And also within the event which happens in the PIC microcontroller also is responsible timing control is provided by the timer circuit, that is three timer circuit which is used in the PIC microcontroller. For example, they given the reception of a character by its UART, universal asynchronous receiver transmitter. UART is nothing but universal asynchronous receiver transmitter. So receiver transmitter, this is nothing but ஒரு என்ன சொல்றது serial data transmitter, okay, as well as receiver, which will be transferring the data and receiving the data with the microcontroller. For this purpose also your timer circuit will be counting the time, okay. For event the need a response faster than the a 10 millisecond loop time. Polling to look for the event every 10 millisecond is not satisfactory. That means if you are using any external device, for example UART they given here, UART what it will do, it will send the data or receive the data through the UART device, you will be receiving the data to the, or sending the data to the PIC microcontroller. Okay. So for every time you will not seeking that 10 millisecond loop time. So it will not be satisfactory to receive or send the data within the 10 millisecond. Okay. In such a case, the event must trigger one of the PIC's many potential interrupt sources. When the interrupt occurs, the CPU will set aside what it is doing in the mainline program, execute the sort interrupt routine to handle the source of the interrupt, and then return to the execution of the mainline program. ஸோ அந்த மாதிரி கேசஸ்லலாம் என்ன பண்ணும், your PIC controller will trigger, okay, any one of the interrupt source. So your PIC microcontroller will have many interrupt sources. அதில் வந்து ஏதாவது ஒன்று ட்ரிகர் பண்ணும். ட்ரிகர் பண்ணி என்ன பண்ணும், the CPU, that is your PIC controller CPU will accept um, interrupt which is coming from the external device. Okay. And it will stop the current program. That current program is nothing but your main program, and it will be start to service the interrupted device. Okay, that interrupted device is nothing but any external device which is seeking request for your with your PIC microcontroller. Okay. So PIC microcontroller will stop doing that main program and execute that interrupt subroutine program. Okay. After completing the interrupt service, it will be returned back to the main program for running or execution. Okay. This is the interrupt of any external device. So, for example, they given here stepper motor. So, an example of such interrupt control occurs when a stepper motor is to be stepped at a rate above 100 steps per second. So, for each interrupt service routine, your timer circuit will be having control. Okay, it will be measuring the time period taken for doing the service for the interrupt service. Okay, interrupt external interrupt. So for a stepper motor that can be started and stopped on a dim at a stepping rate of 150 steps per second. So ஒரு செகண்டுக்கு per 150 steps are taken for rotating your stepper motor. So one of the PIC's timer can be used to generate an interrupt every 6.67 milliseconds. So PIC timer will generate the interrupt um, for every 6.67 millisecond for rotating your stepper motor. Okay. The interrupt service routine can execute the very few instructions needed to check a variable and then take a clockwise step if the variable is positive, and take a counterclockwise if the step variable is negative. So for every instruction, your if a interrupt occurs by the stepper motor to the PIC microcontroller, then PIC microcontroller timer, what it will do means it will fix the time. Okay, interrupt time for every 6.67 millisecond for operating that stepper motor device. Okay, if your instruction has positive variable, then it will be rotating the stepper motor in clockwise direction. If it is negative variable, then negative variable in the instruction, then your stepper motor will be run in the counter, that is anti-clockwise direction. Okay, 1 second. So based on the variable present in your instruction, it will be the stepper motor will be run clockwise or anti-clockwise. Okay, and finally, on incrementing and decrementing the variable present in the instruction, it will be reaching the zero value approximately. Okay, finally. So the overall effect of dealing with event timing in this way is illustrated in the figure. Now we are going to see the peak resources, how it is